Good morning. So today we will solve some examples. Actually, two examples. One example for the reheat Rankine cycle. Another example for the regenerative cycle, just to see how we can calculate enthalpies for both of these cycles in order to calculate the thermal efficiency for each one of them. The first example we have, this is the reheat Rankine cycle. So again, this one says we have steam. We have steam power plant operating on the ideal reheat Rankine cycle. We have steam enters the high pressure turbine at 15 megapascal, 600 degrees Celsius. It's condensed in the condenser at 10 kilopascal. So this is the condenser pressure. If the moisture content of the steam at the exit of the low pressure turbine is not to exceed 10.4%. So this is very important, the moisture content. This is the first time we see this kind of information in problems, and we will see what this means right now. So the moisture content of the steam exit the low pressure turbine not exceed 10.4%, determine the pressure at which steam should be reheat and thermal efficiency of the cycle. Assume the cycle is reheat to the inlet temperature of the high pressure turbine. So in any problem you will have like statement like this one. One of the things I recommend to be able to solve the problems is to be able to memorize the shape of the TS diagram for each one of them. The TS diagram for Rankine or the TS diagram for reheat or regenerative. So for example, this is the TS diagram, the general one that we have for Rankine, the reheat Rankine cycle. So for this diagram, we know that we have 6 points. Each point represents like one thing. So we have point number 1. This one represents the inlet to the pump. Point number 2, this is the outlet of the pump, and this is the inlet to the boiler. Because whatever comes out from the pump, this will go to the boiler. Then we have point number 3, this is the exit of the boiler, and the exit of the boiler will go to the low pressure turbine. So this one represents the inlet to turbine 1. Okay, and this is not the low pressure turbine, this is the high pressure turbine. Turbine 1, high pressure turbine. Then point number 5, this is inlet to the reheat or the reboiler again. This is the boiler. So this is inlet to boiler for reheat. Then point number 5, this one, this is the inlet to the second turbine, which in this case, this is the low pressure turbine. And the last point, point number 6, this is the inlet to the condenser. So it's very important to know which point represent the inlet to each equipment or the outlet to each equipment. So point number 1, inlet to the pump, and this is the outlet of the condenser. Point number 2, outlet of the pump, which is inlet to the boiler. 3, inlet to the first turbine, outlet of the boiler. 4, as we said, this is the outlet of the first turbine or inlet to the boiler. 5, outlet of the second turbine, outlet of the boiler after the reheat cycle or inlet to the second turbine. 6, this is the inlet to the condenser or outlet of turbine number 2. So it's very important for each point to know which this point represent inlet to one point and outlet of another point. So this is very important to know what is the inlet or outlet represented by each point, because based on the data, then you will put your information. So similar to here we said we have steam enters the high pressure turbine. Okay, so we need to talk about the high pressure turbine. So this is the high pressure turbine, point number 3. It's 15 megapascal, 600 degrees Celsius. So now based on this like condition, I know what is the temperature and pressure at point number 3. In the example, he will not tell you that the pressure and temperature at point number 3 is this megapascal or this temperature. Just he will say, this is the conditions at the exit of the turbine. This is the conditions as the exit of the condenser. So this is very important for you to know where this point located, what is the number of this point, so in order to know this one. So based on the conditions, now I know that at point number 3, the pressure at point number 3 is 15 megapascal. Temperature at point number 3, this is 600 degrees Celsius. Then he said we have the condenser pressure is 10 kilopascal. So this is 10 kilopascal. This is the line that represents the condenser. So pressure at point number 6, pressure at point number 1, both of them, the pressure at both points is 10 kilopascal. Then the last information here, the moisture content at the steam at the exit of the low pressure turbine. So what is the exit of the low pressure turbine? Point number 6. Point number 6, because 5, 6, this path representing the low pressure turbine. So this is the exit of the low pressure turbine. And here he's saying the moisture content at this point, at point number 6, is 10.4. Moisture content, this is the fraction of the liquid we have. Because you see point number 6, it's mixture of liquid and vapor, right? So here given, he tells you what is the fraction of the liquid we have. Usually, do you remember in the equations, we use Q, quality. And equality represents the fraction of vapor, not the fraction of liquid, okay? So since we have liquid and vapor, so the summation of both fractions is 1 or 100%. So if I know that the moisture content is 10.4, so the fraction of vapor is 100 minus 10.4, then you can calculate the quality. So there is no need to use any appendix to substitute in the quality equation to calculate it. You already can find this information based on the given what we have here. Is this clear? Okay. So this is what we have based on the given information, and then we can put it on the figure, and then after that we start like doing the calculations. If we start doing the calculations, so as we said, the goal of all of these problems is to find the thermal efficiency of this cycle. So the thermal efficiency of this cycle for ideal reheat Rankine cycle the thermal efficiency is 1 minus Q out divided by Q in. The same equation if you have Rankine, if you have Carnot. Carnot, just with the exception, we can use the temperatures. But if you have Rankine, if you have reheat Rankine, regenerative Rankine, the same equation. But what will be different? How we can calculate Q in, how we can calculate Q out. So for this one, we have Q out. This is H6 minus H1. So the enthalpy at point number 6 minus enthalpy at point number 1. Because this is what is happening in the condenser, and the condenser, this is the path that representing the condenser. Or if you can see, this is the condenser I have, the inlet is point number 6, outlet is point number 1. So just the enthalpy difference between the inlet and outlets of the units. We have Q in. If you remember from previous lecture, what are the steps, how many steps we have in which we are adding heat to the working fluid? 2 steps. One in the boiler between step number 2, step number 3, and another one in this reheat. So we have 2 delta H's will be added. So we have the first one, H3 minus H2 plus H5 minus H4. So if you can calculate these enthalpies, substitute in these equations, calculate Q in, Q out, substitute in thermal efficiency, and then you can find thermal efficiency. Clear? So now the point, how can we start? Now I have some information at point number 6. I have information at point number 3. I have information at point number 1. These are the given information I have in the example. So I can start by any one of them. If we start by point number 6, so point number 6 or state 6, we have mixture of liquid and vapor. But I know that this point, the pressure at this point is 10 kilopascal. This is given because he said that the condenser pressure is 10 kilopascal. And also we have Q is 1 minus 0.104. So the quality, this one will be 0.896. So remember that the quality represents the fraction of vapor, moisture, the fraction of liquid. Okay? Okay. So we have this one. So what we should do, so this is what we start with. This is the pressure we have. So you can go to the appendix and find the following. So we can say from the appendix, assume that you have saturated liquid at 10 kilopascal. And based on this, find the specific enthalpy of liquid and only a specific enthalpy for liquid. If we don't have the quality, then we should calculate the specific entropy for liquid. Then assume that we have saturated vapor at 10 kilopascal and calculate specific enthalpy for vapor. So this is the starting point we have. We have given pressure. If we have saturated liquid at this pressure, what will be the specific enthalpy? If we have saturated vapor at this pressure, what will be the specific enthalpy? And again, keep this in your mind. If we don't have the quality, then for this one, we should find what is the specific entropy for liquid, specific entropy for vapor. These two information I need in order to calculate quality. But this example, the quality is given, so I didn't calculate or find these two values. Okay, so this enthalpy, like used to find quality value. But again, it's given in this example, so we didn't find the entropy for liquid and vapor, only enthalpy will be fine. Okay, so for this one here, okay, or let me, no, we have one more, okay, okay, then we can substitute in this equation that calculates enthalpy. So the enthalpy at point number 6 will be enthalpy of the liquids plus Q enthalpy of vapor minus enthalpy of liquid. So based on the numbers we have here, this is what we got from the appendix. So we have HL, this is 191.8 plus quality, which is 0.896 times H vapor minus H liquid, 2392.1. So you can substitute here, and here we will find enthalpy at point number 6. That will be 2335.1 kilojoule per kilogram. So now I calculate enthalpy at point number 6, and this is one of the enthalpy I need to calculate the Q in and Q out. Okay. Then we can have or continue the following. We have point number 1 or state number 1. I know it's saturated liquid at 10 kilopascal. And this is everything we need to know at this point. So again, from appendix, I can find enthalpy at point number 1. And by the way, this will be the same as enthalpy of the liquid, which is 191.8 kilojoule per kilogram. Point number 1 will help us to know enthalpy at point number 2. This is the pump step, so always find specific volume at point number 1. So specific volume, this one will be 0.0101 meter cube per kilogram. And again, this is enthalpy at point number 1, which I need here. So now based on these T information, I can use enthalpy at point number 1, enthalpy at point number 6, substitute in Q out equation, and then you can say this one equals 2335.1 minus 191.8. So this equal 2143.3 kilojoule per kilogram. So now we know one value of this. At least we know Q out. Okay? Just if you can find Q in, then you can calculate thermal efficiency. And this is everything we need. Okay. So let's continue the solution we have here. So we have number 1, state number 1. We can use it to find the state 2. So state 2 in order to find the conditions of this one, okay, for state number 2, okay. So state number 2 is subcooled liquid at, sorry, this is state 2, not 3. At P2. We know that we have the equation that the pump work, this is H2 minus H1 equal specific volume at point number 1, pressure at point 2 minus pressure at point number 1. So what we have given in this information, I know that point number 1, the pressure is 10 kilopascal. Specific volume, we just calculated it when we were doing state number 1, 0.00101 meter cube per kilogram. H1, we have it 191.8 kilojoule per kilogram. But we have no idea about H2. We have no idea about at this pressure, the pressure at point number 2. But what we know here, we know that the pressure at point number 2 equal pressure at point number 3, right? So let's try to more understand this diagram we have. So let's put some notes here. So we know that pressure at point number 2 equal pressure at point number 3. Okay. So what else we can conclude? We know that temperature at point number 3 equal temperature at point number 5. They are at the same horizontal line, right? We know that the entropy at point number 3 equal entropy at point number 4. Because this process, the expansion we have in the turbine is isentropic. Also the other turbine, low pressure turbine 5-6, so we have the entropy at point number 5 equal entropy at point number 6. So these are some other notes, some other observations that we know from the graph. So in order to find enthalpy at point number 2, we need to find the pressure at point number 2, but we don't have any information to find it. But we know that pressure at this point equal pressure at this point. So we can if we're able to calculate pressure at point number 3, then automatically we can find pressure at point number 2 and find H2. And also we have all of these other observations that we can find. So let's get back to this one. So far what we did, so far we analyzed the state number 6, we analyzed state number 1. These are the two things we have. State number 1, only we will use it to know the information at point number 2, and now we are stuck because we don't have the pressure at point number 2. So we will get back to point number 6 and the other information at point number 3, because these are the information that we don't have. So let's get back to the given thing we have in this example to say, we have given that the pressure at point number 3, this is in the example, was 15 megapascal, and temperature at point number 3, this is 600 degrees Celsius. And at point number 3, we have superheated steam. So now I have pressure at point number 3, and the pressure at point number 3 will be the same as pressure at point number 2. So pressure at point number 2, this one will be pressure at point number 3. This will be 15 times 10 to the power 3 kilopascal. So now I can substitute in work pump equation, and from this equation I can find enthalpy at point number 2, and the number I will have is 206.95 kilojoule per kilogram, and this is one more enthalpy I was able to calculate. So this is H2, and if we return to this one here, this is H2. So we still have H3, H4, H5. We still need this information. Okay, so far is clear? Okay. Now we can continue state number 3. For point number 3, we know that we have superheated steam. At 15 megapascal and 600 degrees Celsius. So now if you can go to the appendix, or the Excel file that we shared with you before, just put the numbers and you will find that enthalpy at point number 3, this is 3585.1 kilojoule per kilogram. Okay. And here we have information that entropy at point number 3 equal entropy at point number 4. So calculate entropy at point number 3. So entropy at point number 3, this will be 6.6796 kilojoule per kilogram Kelvin. So now again I have a new enthalpy value. This new enthalpy value for H3, and if we return to the equation we have, I will find I have H3 here. So now I still have enthalpy at point number 4, enthalpy at point number 5. These are the information I have. So if we get back to point number 4, what I have at point number 4 is that, okay. So now I'm missing point number 4, point number 5. So let's see what we have now. So now we have 2 points. We have state 4. This one is superheated steam. What I know at this point that the entropy at point number 4 equal entropy at point number 3 equals 6.6796 kilojoule per kilogram Kelvin. I don't know what is the temperature at this point, okay, but I know that the pressure at point number 4 equal pressure at point number 5. That's also I can add here. Pressure at point number 4 equal pressure at point number 5. This is everything I have. So if you have superheated steam and you know only one information, then you cannot continue making any calculation for this one. We need one more information. So the information we have here can be pressure at point number 5. If we know pressure at point number 5, then we can have the same value for this pressure and then at point number 4, and then we can calculate it for this one, for point number 4. Also what we have for state 5, we know that for state number 5, I know the temperature. I know that temperature at point number 5 equal temperature at point number 3, and the temperature we have for point number 3 is 600 degrees Celsius. And the other information, I know that the entropy at point number 5 equal entropy at point number 6. And I don't have this one. And again, point number 5 is superheated steam. So how many information I need? 2. So the key here, you need information at point number 5. This will help you to find the information at point number 4. But point number 5 itself is missing some information, and point number 5 is related to point number what? Point number 6. So let's get back to point number 6. So let's return to state 6. And now what I need to find for state 6 is entropy at point number 6. We did some calculation for point number 6 before, right? And all of this calculation is we have this equation to find enthalpy for point number 6. So the same equation will be used. Any point in the mixture, we have the same thing that will be applied. So it will be entropy at point number 6 equal entropy of liquid plus quality times entropy of vapor minus entropy of liquid. So this is why if we get back here, so we know that we need to find this S of entropy of vapor and entropy of liquid. So entropy of vapor and entropy of liquid, based on the previous examples, we only need them in previous examples to calculate Q. And here in this example, we have one more thing, that we still need them in order to calculate Q. This is one thing, but even if Q is given, so we still can use it to find entropy at this point. And this is one important thing for a Reheat Rankine cycle. Okay, so we have S of liquid, we have S of vapor, so we have this equation, S of L. This will be specific entropy of saturated liquid at 10 kilopascal, condenser pressure, plus Q, S of vapor minus S of liquid. If we put some numbers here, so we will have 0.6492 plus Q 0.896 times delta S 7.4996. Then the entropy at point number 4, this one will be 7.3688 kilojoule per kilogram Kelvin. So now I get entropy at point number 6. Now get back to state 5. So state 5, superheated steam. Temperature 5 equal temperature at 3 equals 600 degrees Celsius. Okay. Entropy at point number 5 equal entropy at point number 6 equal 7.3688 kilojoule per kilogram Kelvin. So now superheated steam, two information available. So now I can use the steam table in order to find the specific enthalpy at point number 5, which is 3674.9 kilojoule per kilogram. And also I can find pressure at point 5, and the pressure at point 5 will be 4 megapascal. I have one more enthalpy now. I'm able to calculate this one. So this is the value of the enthalpy, H5. So if we get back to the equations, now I have this H5. So I'm only missing H4. So now I go back and continue to state 4. State 4 also as superheated steam. And for this superheated steam, we have pressure at point 4 equal pressure at point 5 equal 4 megapascal. Entropy at point number 4 equal entropy at point number 3 equal 6.6796 kilojoule per kilogram Kelvin. Then I can go to the appendix or the Excel file I have, and I can say then the enthalpy at point number 4, this will be 3155 kilojoule per kilogram. And again, this is a new value of enthalpy that I calculate. Okay. And again, if we get back to the equation, this is the last enthalpy that I need to find. So now I have all the enthalpy values I calculated, so I can substitute all these values to calculate Q in and Q out. So I have it here. Then substitute in Q in and Q out equations. Then we calculated Q out, that is equal 2143.3 kilojoule per kilogram. Also we have the equation, we substitute enthalpy values to calculate Q in, that will be 3869.1 96.1 kilojoule per kilogram. Then substitute in thermal efficiency equation, and based on this one we can see the thermal efficiency of this regenerative cycle will be 0.45, or in percent this will be 45%, and this is the requirement that I need to calculate. Clear? So the whole idea in this one, just try to find the enthalpies that you need to calculate in order to find thermal efficiency. Again, know that how you can use the steam tables. If you have saturated liquid, if you have saturated vapor, you just need one information. If you have subcooled, superheated, you need two information. And here we have like these notes based on our understanding of the process. So I can have pressure at some point can be the same pressure at another point. Entropy at one point can be the same as another point. So all of these observations or these notes we have there, this is based on understanding of the changes or the processes we have in the cycle. Okay? So without these things, we cannot proceed. because as you can see, we use entropy at point number 4 to find data at 3, because they have the same entropy. Entropy 5, entropy 6, they have the same entropy. Okay, so this is very important that to keep these notes in your mind. Questions? Okay. We're supposed to solve another example. This is for the regenerative, but I doubt that we have time for this one.